Hello friends, today we will start with a new topic or a new module of 5 lectures that is on constitutive analysis. Okay, so sometime we say constitutive analysis, or you can hear maybe term called constitutive equation or constitutive model or modeling. So constitutive model means the basic idea on which you have developed the analysis or the equation. Okay, so this analysis equation model will be interchangeably will be used in this particular lectures. Okay, so what do we mean by constitutive analysis or constitutive equations? Okay, so constitutive equations are relationships basically, okay, between stress, strain rate and temperature. Okay, so you take, and it can be between any of the two this variable, between stress and strain, okay, or it can be between stress and strain rate, or it can be between stress and temperature, or you can combine all strain rate and temperature and relate it with the stress. Okay, so the relationship between the stress and these parameters, okay, that is what we call as constitutive equation. Okay, so wherever you hear about constitutive, it will be dealing with these parameters. Usually, and we will see in it in more detail. Okay, there are different type of models. The most popular ones, one is the phenomenological model. Okay, we will see what do we mean by phenomenological. Okay, and these are empirical in nature, because the actual process which is taking place is so complex. Okay, so you cannot kind of get an equation from the first principle. Okay, so usually in hot deformation especially, because of the complexities of the processes which are taking place. Okay, so you are having dislocation generation, you are having dislocation recovery, okay, and then you have dislocation glide, dislocation climb. Okay, so and vacancies are there, solutes are there, they are also diffusing. Okay, so there are so many effects which are kind of combining together, that making a simplified model or making a first principle model, okay, is very difficult process, okay, to account all these effects in one equation. So what is usually practiced is that you develop empirical relationships. Okay, and how it helps. Okay, so constitutive equation, when you develop for any material, okay, it will help you to first understand the what kind of metallurgical processes are going on in the material during hot deformation. Okay, so it will tell you about the mechanical behavior under high temperature deformation. Because we are talking about high temperature deformation, it depends on what type of deformation you are doing. So it will tell you something about that. Okay, and the another thing is, it will be able to tell you about the, or it will be able to help you in developing a, for example, a FEM model. Okay, so suppose you want to develop a model for your hot rolling or extrusion or forging process. Okay, so to develop that model, you need this constitutive equation, okay, to tell the model that how the material is going to behave under these conditions. Okay, so you will apply the boundary condition and mechanics on the model, okay, by putting constraint. Okay, this is how the deformation is going on, but you also have to put in that how the material is going to behave under those imposed condition. Okay, and that will be told by the constitutive equation. So that constitutive equation has to go in at the appropriate place for proper modeling. So depending upon how you are developing the constitutive equation, okay, your modeling will be of that level. Okay, that it will be able to predict all the stresses, strain rate during the deformation accurately, if you have a accurate constitutive model. Okay. Now there are different type of constitutive models, as I was telling you. Okay, phenomenological is very popular. In this, flow stress is predicted based on empirical observations. Okay, so as the name suggests, it is kind of, you understand the phenomena. Okay, and applying some logic, you are using those ideas to develop a empirical relationship. Okay. So, which parameters to consider, which parameter to take in the numerator or denominator, okay, that will be decided by the phenomenology or phenomena which is taking place, okay, and that will give you a cue that what type of equation has to be developed. Okay. So, while doing the empirical analysis, you have to find out that what is the relationship between different parameters, okay, so that when you put it, you will be able to develop a empirical relationship between them, and you will get ultimately some mathematical function. Okay. And of course, it is usually developed for different temperature ranges and strain rate ranges, because the material behavior changes as a function of strain rate or temperature. Okay. At lower temperature, you can see that only you have dislocation glide as the deformation mechanism. As you go to high temperature, you also have dislocation climb, and then the diffusion of self diffusion and solute diffusion and so on. Okay. So, your material behavior changes. So, you develop the constitutive equation for different strain rate range and temperature ranges. Then there are some physical based constitutive model, which is based on the actual processes which takes place during the deformation. So, the physical aspect of the material behavior is considered. For example, dislocation generation or dislocation recovery, how dislocations are directly taking part in the deformation process. So, basically that is what you try to develop through first principle in this case. So, using theory of thermodynamics, thermally activated dislocation movement and kinetics. Okay. But because as I told you, it is not a very clear picture where you can easily get this equation from first principle. So, it required large number of constants to fit the equation, okay, or to get your required constitutive equation. Then nowadays a very important technique which is coming up is called artificial neural network, okay, ANN models. Okay. The importance of ANN model is that you do not have to understand the actual metallurgical process. Okay. So, basically you have some input data and you have some output data. So, input data will be in form of a strain rate and temperature, for example, and output is in the form of stress. So, you have these parameters, these are input and you have some output. So, basically you train the ANN model, okay, using this data, okay, and then you try to predict that at any other condition what will be the stress. Okay. So, the ANN models are also gaining lot of importance. Mainly the importance which it is gaining because when you develop this phenomenological or physical based constitutive model, the problem is that all your this response in terms of stress is non-linearly dependent on the temperature and strain rate. Okay. Whenever we develop empirical equation, okay, we try to make or we try to make a graph between the response and the input parameter, so that we get some linear curve, okay, because in linear, when you have linear curve or linear straight line, okay, it is easier for me to do a regression analysis and get an empirical equation. Okay. If it is a non-linear function, then it is a very difficult one to find out whether it is a exponential curve or parabolic curve or hyperbolic curve or so and so on. Okay. But in a straight line, I can easily, using best fit line, I can find out whether how much this straight line is close to the actual data. Okay. So, you want to have some linear relationship whenever you develop the empirical relationships, but our stress and the response is actually non-linear as a function of temperature and strain rate. That is why developing these empirical relationships are difficult, and you have so many models to do that. So, ANN helps there, because it is not worried about all these problems of non-linearity. It fits lot of polynomial equation between these parameters, okay, and do something in that black box which we call as ANN model, and give you the output. Okay. Only problem with ANN model is that you will not be able to understand the material behavior from that. Okay. And why that is important? That is important because when you are designing a material, okay, if I do not know the material behavior, how I am going to design it. Okay. So, that is the only problem with ANN model, that I will not be able to get a clear picture about the material behavior, that how material is behaving or what parameter is controlling the response. That will be very difficult for me to understand from ANN model. Okay. So, I will not get a very good first hand experience of the material. However, you have very good accuracy of flow stress predicted by these models. Okay. Whereas, with regression analysis developing this empirical relationship, you have lower accuracy. Okay. Now, to give you a feel of constitutive equation, okay, one of the most familiar constitutive equation you must have come across is Hooke's law. Okay. So, that is also a constitutive equation, just to take the fear out of this particular term. Okay. So, basically in that what we do is we relate stress with the strain, very simple equation. Okay. And basically you can see that it is already linear, okay, because when you have plot of stress and strain in the elastic regime, okay, it is a straight line, okay, a linear behavior in the elastic regime, and the slope of this particular line gives you the Young's modulus. Very simple equation, and it is already linear because the curve starts from 0, you do not have a constant here. So, it is an equation of this type, okay, where only this particular term is there, okay, and this term is 0. Okay. So, it is a constitutive equation, already a linear equation, very simple to understand, okay, and the slope gives you the Young's modulus, straightforward, I can get it. Okay. Now, to coming to hot deformation, okay, basically first process which you do is to generate data. Okay. So, whether you do phenomenological modeling, or if you do physical based modeling, or you do NN modeling, first you have to find out that what is the response of the material to different parameters. Okay. So, the first thing which you do is generate data, okay, and if you generate good quality of data, your model will be that much accurate. Okay. So, you should pay utmost attention during this process, that data generation, or it should be all the experiments should be done religiously. Okay. You should not take any shortcut here, do a good experiments. Okay. If in any experiment, suppose you are not sure about that the deformation was progressed properly, do another one. Okay. Because the amount of work which you put in here, okay, that will kind of reflect in your constitutive equation. Okay. So, first thing is always to put maximum attention and maximum care to develop or to get the data for your constitutive equation. Okay. So, in high temperature deformation, there are two very important parameters. Okay. These are strain rate, okay, and temperature. So, you have these two as the main input, okay, and of course, output is your stress. Why we do not consider strain? Okay, more or less, if you see in high temperature deformation, if it is dynamic recrystallization also, if it is only having one single peak, that you get a steady state condition. That means, the stress is not changing much with the strain. Okay. For example, you can see in these different curves, okay, different strain levels, more or less stress is constant. So, you have reached a steady state. Okay. If in your flow curve you also are seeing maybe a strain hardening part. Okay. So, it is something like this, for example, then you should also consider strain in this term, okay, because your flow stress is continuously changing as a function of strain. But if it is a steady state, okay, then I would be mainly interested in strain rate and temperature. Okay. So, this you should understand that why most of the time you do not have a strain in this constitutive equation when you are developing for hot deformation. Similarly, if you develop for low temperature, okay, temperature below 0.4 of melting point, you will see that strain rate is not there, okay, because the strain rate dependence of stress reduces as you go to lower temperatures. Okay. So, you will see this effect that constitutive equations are changing as a function of temperature. So, what you do in this data generation, as you can see, you are deforming at different temperatures, okay, and you are deforming at different strain rates. Okay. So, you are generating data like that, deformation at different strain rate and different temperature, and then you will use this input to develop the constitutive equation. Okay. Now, what important material parameters you will be trying to find out here is basically if it is your stress is function of strain, then strain hardening coefficient. If your stress is function of strain rate, then your strain rate sensitivity. If your stress is function of temperature, okay, activation energy for deformation. Okay. So, these three are very important material parameter which you want to find out, okay, from the when you are developing the constitutive equation. Okay. So, these and these material parameter actually gives you some indication about that how the material is behaving under the deformation conditions. Okay. So, I will tell you one by one that how you can get these parameters, okay, from the data in a simplified way right now. Okay. Later on you will be able to see during the actual or when you want to develop a comprehensive constitutive equation for hot deformation work, okay, how you can find out these parameter from the data. Okay. Right now I am just giving you the sense of these parameters by doing a analysis. Okay. So, the strain hardening, okay, I think we must have seen earlier also that stress is a function of strain, okay, and it is a exponent, there is a exponent on the strain term. Okay. So, it has some exponential type of behavior. So, if you remember, we just drew it earlier also that this is the linear part, after yielding it will have something like this. Okay. So, basically this n is the slope of this exponential curve, okay, some kind of exponential curve is this. Okay. And how to find out this exponent n? Okay. So, basically you can find out the at different strain levels what is the value of stress. Okay. So, you have epsilon 1, epsilon 2, epsilon 3, sigma 1, sigma 2, sigma 3 and so on. Okay. So, now if you see this particular equation, if I take logarithmic on both the side, okay, it will the exponent will come down here. Now, it will be something like this. Now, it becomes a linear equation. As I told you that whenever we want to develop empirical equation, I want to linearize the particular equation, so that whenever whatever parameter the k parameter and the n parameter I get from the equation, I can easily say with surety, okay, this is the best fit straight line I am fitting and this is the regression coefficient. Okay. How close it is to the value of 1, that gives me the confidence in the constitutive equation. Okay. So, for example, now I will be plotting ln epsilon versus ln of sigma here, and of course, you will get some points like this. Okay. I am not sure. Okay. And then I will fit a straight base fit line to this. Okay. So, the slope will be equal to n and the intercept will be equal to k. Okay. So, of course, it will be log k here and you have to take anti-log of that. Okay. So, this slope will be n, okay, and this will be your constant C. So, doing a simple analysis like this, I will be able to get the strain hardening coefficient, which is n here. Similarly, you can do for strain rate sensitivity. Okay. If you see a general form of constitutive equation for high temperature deformation, okay, you will see something like this. Okay. So, sigma is equal to C epsilon dot to the power m, okay, and these are you are getting this for, see, whenever you want to find out a particular constant, okay, you have to make other input parameters as constant, okay, then only you will be able to get the, for example, if you want to calculate strain rate sensitivity, I will keep the strain and temperature as the constant. Okay. So, these two are constant, okay, then only I will be able to find out the strain rate sensitivity. Okay. So, again you can see that there is a some kind of exponential dependence of stress on strain rate. Okay. So, again as we were just discussing, basically what I am going to do for a fixed temperature at some temperature, let us say just for argument sake 500 degrees Celsius, okay, at a temperature of 500 degrees Celsius, okay, I am doing test and finding out the something like this. Okay. So, this is strain rate 1, this is strain rate 2, this is at strain rate 3. So, at different strain rates I am deforming the material at a fixed temperature. So, my temperature is constant. Okay. Now, I want to fix my strain also. So, let us say I want to find out the stress value at a particular strain. Okay. So, strain is now constant, okay, and now I will find out what is sigma value for different strain rates. So, sigma 1, sigma 2, sigma 3, sigma 4. Okay. So, now what I have got for different strain rate, and you can see that as so the strain rate is increasing in this direction. So, as strain rate is increasing, my stress is increasing. So, there is a dependence of stress on the strain rate. Okay. And again I can do the same thing if I take log on both the side. So, log of sigma ln of C C plus m ln epsilon dot. Okay. So, again I have linearized the equation, okay, and now taking all these values, again if I draw epsilon dot ln sigma here, okay, you will get some kind of again data points, okay, and a base fit line, straight line, and the slope will give you the strain rate sensitivity m. Okay. So, as you can see very clearly here, okay, this is basically slope of the curve between sigma and epsilon dot, between ln sigma and ln epsilon dot. Okay. So, you are differentiating that particular one. So, basically you are trying to find out the slope, okay, where your strain and temperatures are constant. So, that already we have taken care. So, because we have taken data only from that. So, this is the way I can calculate the strain rate sensitivity of the material during high temperature deformation. Now, why it is important? Okay. If you see this particular curve here, that as my m is increasing, okay, my elongation is increasing. That means the ductility of the material is increasing as the strain rate sensitivity is increasing. Okay. So, it will be nice for me if I will be able to deform material where the strain rate sensitivity is high. Okay. That way I will be able to have higher, or I can impose more strain in the material because ductility is good. Okay. And as you can see here for different material they have plotted it. Okay. So, as m is increasing, okay, so from 0.2 to 0.6 you can see that the ductility is increasing, and even it is reaching 1000% here, okay, very high ductility. And this is where if you remember I told you about superplasticity, this is where you will be able to say with confidence that it has superplastic or superplasticity is there in the material. Okay. Basically anything above 300% I should be able to say it is superplastic. Okay. And if you see around 300%, my M is coming around 0.3 to 0.4. Okay. And this is what is the definition for superplasticity, that if any material has to behave in a superplastic condition, okay, the strain rate sensitivity should be more than 0.33 or so some people say it should be 0.4. In general it can be above 0.3. Okay. So, you can see very clearly around 300 to 400% if I take as a cutoff for superplastic deformation, okay, or elongation of that kind, you will be able to see the M is in the range of around 0.3 to 0.4, okay, and it should be above that. Then you will be able to see superplasticity in the material. Okay. So, this is how I can calculate the strain rate sensitivity, as I have shown just now in the previous slide, that how I can calculate the strain rate sensitivity, and that is an important parameter during high temperature deformation. I want to have higher strain rate sensitivity for higher elongation. Another very important parameter is activation energy for high temperature deformation. Okay. And again you can see there is some, so now these are very simplified relationships because we are taking other parameters as constant, but when you develop the whole constitutive equation, all these parameters will come together. Okay. So, if you see this particular equation here, okay, sigma is, again there is some constant exponential function is there, and in that you have Q by RT. Okay. And it is, again you can see that we are keeping few things constant here. So, epsilon the strain and strain rate is constant. Okay. So, for this the data or plots which I am going to use will be like this. Okay. So, now I am doing at a particular strain rate, let us say I am doing it at a strain rate of 10 to the power 1 just for argument's sake, okay, or 10, okay, 10 strain rate. And now I am again kind of getting the stress strain curve, okay, for different temperature T1, T2, T3 and T4. Okay. So, my strain rate is constant. So, this is taken care now, and now I can do it for a particular strain here. So, strain is also constant, and for different temperature I will get the stress value sigma 1, sigma 2, sigma 3, sigma 4. Okay. So, this is how I will be able to calculate now the activation energy. So, if you see that the activation energy of deformation, okay, is function as the temperature is increasing, your stress is increasing. Okay. So, as temperature is increasing, 1 by T is decreasing. Okay. So, if I want to take 1 by T here as increasing, my temperature is increasing in this direction. So, at higher temperature your flow stress has to be low. Okay. Sorry, as temperature is decreasing, so it is T1 is more than T2, is more than T3, is more than T4. So, temperature is more in T1 and less in T4, okay, but the stress is higher. So, there is a inverse relationship here. Okay. So, when temperature is more, stress will be low. Okay. As temperature is reducing, okay, my stress is increasing. So, it will have some kind of data like this for stress as a function of 1 by T. So, when temperature is reducing here, 1 by T is increasing here, okay, and that is how the stress is changing. Okay. So, if I plot now again, as you can see, I have done 1 by T, and this sigma I have to take as log, because to make it this equation linear, what I will be doing, again taking logarithm on both the side, it will be something like this C 2 and this is an exponential term. So, basically your q by RT will come like this. Okay. So, now if you see this particular equation, it is a linear equation, this is y, this is your constant c plus 1 by t is your x axis. So, q by r becomes your slope. Okay. So, if I plot a straight line here, now my q by r becomes the slope of this equation. Okay. And this is how I am going to get the r is your universal gas constant. Okay. So, whatever value comes you multiply it by r, then you will get the q in joules per mole. Okay. And testing temperature you have to take in Kelvin. So, if I plot my ln of stress as a function of 1 by t, I will be getting something the plot like this, and from there I will be able to calculate the activation energy for deformation. Okay. Okay, so I have already told you how to calculate the activation energy for deformation. Okay. Now, if you see there are different straight range for different processes. Okay. So, at high temperature also you have large variation of strain rate where you have different type of processes which can takes place. Okay. So, I am just kind of defining here different type of processes, okay, because these we will take later on when we will discuss constitutive equation in more detail. Okay. So, the first one here is that you have at very low strain rate 10 to the power minus 8 to 10 to the power minus 5 strain rate. At that you get the deformation called creep, okay, and that is a very common failure mechanism in any material which is used in high temperature condition. So, at very low flow stresses also, okay, under the applied load structure on the structural material, if it is at high temperature it keeps deforming as a function of time. So, it deforms at constant load or constant stress. Okay. So, creep deformation is a very slow process, time dependent process, but material keep deforming under the a very small applied stress, okay, which can be its own weight, or maybe if it is a moving part under the forces of centrifugal forces or something like that. Okay, it keeps deforming, okay, and what will happen that your dimensions will change after some time for your component, and that will lead to the failure of the material. Okay. So, this is one mechanism which takes place at very slow strain rate. Then the next strain rate range is 10 to the power minus 5 to 10 to the power minus 1, okay, where you actually do a quasi static tension test. So, normal tension test which you do in laboratory, okay, these are usually in this temperature range. For example, for superplasticity also we will be doing when we want to characterize superplasticity we will be doing in this particular strain rate range, okay, or when you do your room temperature tensile test also you do at strain rate of maybe 10 to the power minus 2 or so. So, that is why these are called quasi static. It is not exactly static, it is quasi static, very slow deformation you are doing. Okay. Then comes the another range 10 to the power minus 1 to 10 to the power 2. Okay. Now, you are going to high strain rate kind of regime. These are dynamic tension or compression, okay, and this is where you do basically hot working also. So, all your industrial hot working processes, thermomechanical processing are done in this strain rate range, okay, and this is where I would be doing superplasticity, for example. Okay. Then you can go even ahead furthermore with 10 to the power 2 to 10 to the power 4 strain rate. Okay. These are high speed testing using impact bar. Okay. One of the equipment can be what we call as a split Hopkinson test bar. Okay. So, basically you keep the sample and you hit it with a very heavy rod. Okay. So, the strain rates are very high, okay, and the range for that strain rate is 10 to the power 2 to 10 to the power 4. Okay. Very high strain rate deformations can be possible here. then you can go even ahead with 10 to the power 4 to 10 to the power 8 strain rate. These are hypervelocity impact using gas guns or explosives. Okay. So, very high impact you can have to get through explosive techniques. Okay. So, basically if you want to characterize a armor plate, okay, you should be going for this kind of strain rate, okay, that how the material is behaving under the impact condition. Okay. So, these are the different straight range rate range, okay, in which different type of deformation mechanism are operated or will be operating. Okay. And as I was telling you in the beginning that empirical equations are usually made for particular straight rate range. So, these are the ranges. Okay. So, I will be developing a different constitutive equation for creep deformation, another constitutive equation for a superplastic deformation for example, another type of constitutive equation for hot working kind of problem, even another constitutive equation for even higher strain rate range 10 to the power 2 to 10 to the power 4. So, for different strain rate range depending upon these what kind of actual deformation mechanism which is taking place in the material, you will be developing different set of constitutive equation for these straight rate range. Okay. So, this is how I can find out the straight rate range. So, thank you. With this I have kind of covered the initial part of constitutive equation, what are the important material parameters, straight rate range, and what are the different type of constitutive equation, phenomenological, physical based or through NN type of modeling. Okay. And what parameters you are actually going to find out there, okay, which kind of characterize a particular deformation process. Okay. Thank you.